In this video, we discuss how to use neural tangent kernel (NTK) to analyze over-parameterized neural networks. Over-parameterized neural networks exhibit properties that traditional machine learning theory cannot fully explain. For instance, when the number of parameters becomes very large, these networks don't necessarily overfit the training data. This contradicts the conventional understanding of machine learning, making it necessary to develop a new theory. Neural tangent kernel serves as a tool to establish a theoretical framework that explains the behavior of over-parameterized networks. First, we will outline the topics to be introduced. We begin by presenting the definition of the neural tangent kernel (NTK) and its properties in relation to the training dataset. Next, we will analyze how the convergence of training loss in over-parameterized neural networks can be explained through NTK. Finally, we will explore how NTK can be used to analyze the generalization of testing loss. This demonstrates that even with a large number of parameters, the testing error can still be minimized, meaning overfitting does not necessarily occur. Neural tangent kernel originated from the work of Jacotet et al. 2018. It is a kernel operator that computes the inner product of two training instances in a specific kernel space. This kernel space maps the input instance to the partial derivatives of the neural network outputs with respect to the weights. In this context, X refers to the training instance, WLM represents the weight connected to the mth neuron in the ELF layer, and FW indicates the neural network's output with weight W applied to the training instance. There are capitalized L layers and capitalized M neurons in each layer. In over-parameterized neural networks, the number of parameters is extremely large. If we significantly increase the width of the hidden layer, the network will contain a vast number of parameters and become over-parameterized. In the work of Jacotet et al., it was found that if the width of hidden layers, capitalized M, approaches infinity, the neural tangent kernel stays constant throughout the training process. This greatly simplifies the analysis of the neural tangent kernel and can be used to approximate the behavior of over-parameterized neural networks. To calculate the exact value of the neural tangent kernel, the work of Arora, Sanjeev et al. Introduces a two-layer neural network that is easy to analyze. There is a simple closed-form solution for the neural tangent kernel which can be easily derived and evaluated, as demonstrated below. This two-layer network contains two types of parameters. The symbol W represents the trainable weights connecting the input layer to the hidden layer. The symbol A is initialized randomly and remains fixed during training, connecting the hidden layer to the output layer. With only one layer of trainable weights and the nonlinearity in the hidden layer, this closed-form solution of the neural tangent kernel can be derived while preserving the expressiveness of the neural network. We now introduce the properties of the neural tangent kernel under different data distributions. Given n training data points, we can apply the kernel operator H pairwise to the training data. As a result, we obtain an n by n matrix known as the Graham matrix, whose elements represent inner products in the kernel space. Since this matrix is symmetric, we can perform eigendecomposition to break it down into a diagonal matrix multiplied by an orthogonal matrix and its transpose. These three matrices can be further expressed as the sum of the eigenvalues and eigenvectors of the Graham matrix. The diagonal matrix contains the eigenvalues of the Graham matrix. The orthogonal matrix contains the eigenvectors of the Graham matrix corresponding to the eigenvalues in the diagonal matrix. Here we present examples of the Graham matrix. In this example, the input instances X can be clearly divided into two distinct groups. The values in the Graham matrix are calculated using the closed-form solution of the neural tangent kernel for a two-layer neural network. By performing eigendecomposition, we obtain the eigenvectors and eigenvalues. It is important to note that one eigenvalue dominates the others. This indicates the existence of a dimension that can clearly separate the two groups of data. In another example, the input instances X do not exhibit clear separation. Using a similar approach, we can obtain the eigenvectors and eigenvalues of the Gram matrix. In this case, the eigenvalues are comparable to one another, and no single eigenvalue dominates the others. This suggests that there is no dimension from which the two groups of data can be clearly distinguished. In this example, we take the label y into account. We first consider a scenario where y is correlated with x, meaning x can be clearly divided into two groups that correspond to the label y. In this case, the input instances with label 1 are located in the upper right, while those with label -1 are in the bottom left. Using a similar approach, we obtain the eigenvectors and eigenvalues of the Gram matrix. We also compute the inner product of the vector y with each eigenvector. There is one dominant inner product value, and the corresponding eigenvector is associated with the largest eigenvalue. This indicates that y is aligned only with the eigenvector corresponding to the largest eigenvalue. In another example, although x can be separated into two groups, y is not correlated with this separation of x. In this case, the input instances with label 1 can appear in both the upper right and bottom left, as can the instances with label -1. Using the same approach, we obtain the eigenvectors and eigenvalues of the Gram matrix, as well as the inner products of vector y with each eigenvector. There is no dominant inner product value, and most of the inner products have comparable magnitudes. This indicates that y is not aligned with any particular eigenvector, making it difficult to separate the input data based on the primary eigenvector of the Gram matrix. We present the results of eigendecompositions of the Gram matrix calculated from real data. Here we show two examples, MNIST and CFAR. The blue line represents the eigenvalues of the Gram matrix sorted in decreasing order. The red and cyan bars correspond to the inner products of the MNIST and CFAR labels with the eigenvectors associated with the decreasing eigenvalues. The red bars represent the original labels of MNIST and CFAR. The cyan bars represent labels that have been replaced by random noise. First, we consider the MNIST dataset, which has simpler features compared to CFAR since it consists mainly of white digits on a black background. These simple features allow the classification of digits in MNIST, meaning the original label y aligns with only a few eigenvectors. This is reflected in the plot, where the red bars show high values for only a few of the larger eigenvalues. The CFAR dataset, on the other hand, has more complex features, including colorful images of vehicles and animals. Classifying CFAR requires more features, so the label y has projections onto more eigenvectors. This is evident from the plot, where more red bars have higher values compared to MNIST. For the noisy labels, which are not aligned with any particular features in either MNIST or CFAR, the projections are spread equally across all eigenvectors. Here we analyze the convergence of the loss function. We assume that gradient descent with a learning rate eta is used to update the weight w in order to minimize the loss function. Let wk represent the weight at iteration k. The training error is defined as the L2 distance between the label and the network output at iteration k, denoted as fwk of x. This training error will converge to epsilon, as shown by the following equation. On the left side, we have the training error, while on the right side we have the square root of the sum of the inner product of y with each eigenvector vi multiplied by a term involving the eigenvalue lambda y. Since the product of the learning rate eta and the eigenvalue is less than 1 as k increases, the term inside the square root decreases. In the plot, we show the left-hand side of the equation in purple and the right-hand side of equation in green. The x-axis represents the number of iterations k, and the y-axis represents the error. The difference between the training error and the term with the square root is epsilon. As the term with the square root diminishes with increasing k, the training error will eventually decrease to at most epsilon. Thus, this equation demonstrates that the training error converges to epsilon as the number of gradient descent iterations increases. We further analyze the term involving the eigenvalues lambda I raised to the power of 2k. This term forms a geometric sequence, decreasing by a factor of 1 minus eta lambda raised to the power of 2. Since the product of eta and lambda is less than 1, for a given I, if lambda I is larger, this term decreases more rapidly. Conversely, if lambda I is smaller, the term decreases more slowly. Therefore, the eigenvalue lambda I of the Gram matrix plays a crucial role in controlling the speed of convergence during the training process. We now consider another term, the inner product of y and vi. Since all vi are unit vectors due to the symmetry of the Gram matrix, the inner product between vi and y can be interpreted as the projection of y onto vi. If y has larger projections onto the eigenvectors with large eigenvalues, the convergence will be faster. Conversely, if y has projections uniformly onto all eigenvectors, the convergence will be slower. Thus, whether the label y aligns with eigenvectors corresponding to large eigenvalues significantly influences the convergence speed. We present an experiment to demonstrate how the projections of labels onto the eigenvectors affect the convergence speed. The red line represents the original label, which aligns with the eigenvectors corresponding to the largest eigenvalues, resulting in faster convergence. The cyan line represents the noisy label, which projects uniformly onto all eigenvectors, leading to slower convergence. Compared to MNIST, the CFAR dataset has more complex features, causing the projection of y to be distributed across more eigenvectors, resulting in a slower convergence speed compared to MNIST. These experiments show that the alignment of labels with input features, as well as the complexity of the input features, can significantly influence the convergence speed. Next, we consider the theoretical explanation of generalization in over-parameterized neural networks, specifically whether we can demonstrate that the testing error will remain small after training. We define epsilon of Fw as the testing error of the model Fw. Epsilon of Fw can be upper bounded by the L1 loss, and the L1 loss itself has an upper bound, as shown in the following equation. In the numerator, we have the inverse of the Gram matrix multiplied by the transpose of y and y. This can be decomposed into the inverse of the eigenvalues of the Gram matrix multiplied by the inner product of y with the eigenvectors of the Gram matrix. This analysis is similar to the case of convergence, with the only difference being that the eigenvalues are inverted. If y aligns with the eigenvectors corresponding to larger eigenvalues, the inverse of these eigenvalues will be smaller, leading to a smaller testing error. Conversely, if y projects uniformly onto all eigenvectors, the sum of the inverted eigenvalues will increase, resulting in a larger testing error. In the denominator, n represents the number of training instances, so the testing error decreases as the number of training instances increases. To demonstrate the upper bound of testing error on real datasets, we present results for the MNIST and CFAR datasets. The x-axis represents the portion of noisy labels, and the y-axis shows the L1 loss or classification error. When the portion of noise is 0, the labels align with the major eigenvectors, leading to a smaller testing error. As the portion of noise increases, the labels tend to project uniformly onto all eigenvectors, which causes the testing error to increase. For the CFAR dataset, which contains more complex features than MNIST, the labels project onto more eigenvectors, resulting in a larger testing error. In summary, when there is more noise or more complex features in a dataset, the generalization performance worsens. To summarize the key takeaways from this presentation. First, the neural tangent kernel can approximate the behavior of over-parameterized neural networks, making it a useful tool for analyzing both convergence and generalization behaviors. In the convergence analysis, the neural tangent kernel demonstrates that even though the loss function may not be convex, it can still converge. Additionally, the convergence speed is influenced by the noise level and the complexity of features in the dataset. Regarding generalization, the analysis shows that the testing error can be small, even as the number of parameters in a neural network approaches infinity. This contradicts conventional machine learning theory, which suggests that increasing the number of parameters leads to a higher risk of overfitting. Furthermore, the testing error is also affected by the noise and complexity of the dataset's features. Therefore, to reduce overfitting in over-parameterized neural networks, it is essential to focus on data cleaning and pre-processing, which can help eliminate noise and enhance relevant features. At the end of this presentation, we provide some further readings. The first paper introduces the definition of the neural tangent kernel. It contains detailed derivations of the concepts and properties of NTK, though it requires a solid understanding of advanced mathematics. The second paper focuses on the analysis of NTK in two-layer neural networks. It includes more concrete examples and is less mathematically intensive compared to the first paper. Thank you for your attention.